I will present a case study from the Glava in Sweden, focusing on how integrating mineralogy, metallurgy, and geochemistry can improve our understanding of mineralization during early stage of exploration. In the earliest stage of exploration, geochemical assays are often the primary source of information. However, the grade alone do not fully explain the nature of a mineral system. So understanding of mineralogical characteristic of ore is essential for smart exploration and development decision. In this project, we focus on global copper project is located in Sweden, and mineralization is controlled by geological features like fault fracture and is mostly related to tectonics. Main research question for this project includes what is the most effective and cost-efficient approach for characterizing copper-bearing mineralization during early stage of exploration, what texture and association characterize copper-bearing mineralization during early stage of exploration, and what grain size and liberation characterize copper-bearing. To address this research question, an integrated workflow was developed that combines heavy liquid separation, autosym-based mineralogy, optical microscopy, and geochemical assay. The objective was to identify the mineral hosting copper and evaluate copper distribution among the mineral phases. This study based on two main hypotheses. The first, we expected heavy mineral, including copper-bearing, concentrated in heavy liquid zinc fraction. Second, we expected a good agreement between geochemical assay result with mineralogical data that obtained from TEMO machine. This presentation covered geological setting, methodology, main result of mineralogy, and key finding. As I said, we focus on the global copper project. 5 representative samples were selected and analyzed using mineralogy, metallurgy, and geochemistry method. Glava, located in Bergslagen, metallurgy province of Sweden, a well-known mining area. Glava is characterized by paleoproterozoic, volcanic and sedimentary rock, and hosts numerous metal-based deposits. So as I said, in this area, mineralogy is controlled by geological features and make this area a good target for exploration. 5 rock samples were submitted for this project, and these 5 rock samples were crushed and screened to make sure we have a particle size consistency, and then split them to make a homogeneous sample for submitting to mineralogy and metallurgy and geochemistry analysis. After obtaining a homogeneous materials, approximately 100 to 150 grams of each sample, proceed using heavy liquid separation at SG 2.95 gram per centimeter, and heavy liquid help us to separate heavy mineral, including copper-bearing minerals, and separate them from light minerals. So heavy liquid give us two product one zinc materials like heavy minerals, and then we have another portion, float part, is gonna be gangue mineral. From zinc portion, we gonna make a polished section, and we studied through the reflected light microscopy. The goal was to identify copper-bearing minerals and study their texture. So as you see, we have copper-bearing minerals here. We have chalcopyrite showing with the yellow one, and we have bornite, arsenopyrite, and also we see bornite exposed to cobalite. And the other picture showing we have bornite that's attached to cobalite, and we have iron-bearing like goethite, hematite as a secondary phases that fill in fracture. We have same copper-bearing minerals in all our sample, but just a bit different in associations and liberation. So I put two pictures from each sample. Copper-bearing minerals are gonna be the same, just different liberation and association. This table shows model mineralogy of 5 samples for zinc fraction. This table showing how much of each mineral we have in these 5 samples. We have bornite, most of the copper bearing, especially bornite. We have the high amount in all of the samples. Also, we have ilmenite as a significant mineral in all 5 samples. And feldspar and silicate are present as a gangue mineral and have dominant amount of gangue mineral. This table shows where copper hosted. In this 5 samples, most of the copper was hosted in bornite. However, one of the samples showing significant copper in chalcocite. This graph showing grain size distribution for all mineral in 5 samples, and also grain size distribution for all copper bearing mineral on the other graph. So both showing the same trends, and we can see we have fine and coarse grain in all of the samples. This graph is again for grain size distribution for bornite and chalcocite. Bornite has same trend in all samples. However, chalcocite has a bit variation in all in 5 samples. And also you can see grain size distribution for ilmenite and hematite magnetite. So ilmenite showing more similarity in all 5 samples, and hematite magnetite has more variation. This grain size distribution help us for next step for recovery, to give them this information for further recovery. This table and graph showing the results of geochemical assay and mineralogical data that's obtained from the TMO have a good agreement that give us more confidence to say, okay, our result is good enough for continuing to next step. table is related to mineral association. It means which mineral occurs together. In this sample, bornite occur with other copper bearing but in different amount, and also ilmenite is more associated with iron oxide. And the other four samples have same. Bornite have more association with all copper bearing, but a bit different in amount. And ilmenite have more associated with iron oxide in all 5 samples. So I'm going to skip. So in summary, copper in all 5 samples was hosted in copper. And also we had a good agreement between geochemical assay and the result that we obtained from TIMO machine. So all of the results are gonna help the client for further exploration. That's all, thank you.